assuming the donkey has a mass of 60 kilograms and is launched with a horizontal component of velocity equal to 40 meters per second, if the cannon has a mass of 200 kilograms and is free to roll, what is the resulting speed of the cannon? So this should remind you maybe a little bit of the recoil example we just looked at, because we're now looking at recoil of this cannon. It's kind of like when we talked about this situation the first time, we explained that donkey was wrong because recoil is perfectly normal and can happen even in systems that have their momentum conserved, and in particular start with zero initial momentum. So in this case, maybe the way I would analyze this is I could say, okay, P final is equal to P initial, and maybe I'll put vector symbols above it here, but we're going to analyze this kind of in one dimension, and if you wanted to, you could write X column, but there's only one dimension here, so I'm just going to do it, right? And I think it's pretty obvious that the initial momentum is zero. I'm leaving a little space here so I can write stuff for the donkey and the cannon, because since I know the donkey is going to be shot off to the right, I think there'd be a positive amount of momentum for the donkey, but there'd be a minus amount of momentum for the cannon. And maybe the way I could then express that is to say, okay, it's the mass of the donkey times the velocity of the donkey minus the mass of the cannon times the velocity or speed of the cannon, if you like. So this is how I like to do things. I mean, I wrote vector symbols up here, but basically I just used an explicit minus sign here to indicate that donkey is going to the right and cannon is going to the left, recoiling to the left, that is, and this is the amount of momentum associated with that. And anyway, so that gives me a formula, and maybe to check to see whether I've actually solved something or not, or if I've got enough physics to do that, is I can recognize that the mass of the donkey is in fact given to us as 60 kilograms, right? The velocity of the donkey, right, is given to us as 40 meters per second, and the mass of the cannon is that relatively large 200 kilograms, and we're being asked for the velocity of the cannon, right? Well, I've got those four variables here. Really, you know, and this is equivalent. Maybe the easier way to look at this is to recognize that if you added the cannon part of the momentum here on both sides, and then I'm actually going to write that part on the left because that'll be convenient, I think, for solving. But I think that this is algebraically equivalent to what I have written up here. And I think it'd be fairly straightforward to, this is the one, right, that I'm being asked for, to isolate that and then plug in the numbers that I know to get an answer. In other words, the velocity of the cannon, the recoil velocity, should be equal to the mass of the donkey times the velocity of the donkey all over the mass of the cannon, and then putting in the numbers. I'm actually going to write this. I was also already tempted to do that when I was writing the formula. Whoops, that's the wrong number. It's 60 kilograms for the mass of the donkey divided by 200 kilograms times the velocity of the donkey. And this kind of makes sense, right? I mean, I'm writing it this way with the 2 kilograms sort of as a ratio, right? The two masses in kilograms as a ratio. It makes sense that the cannon is going to be going slower, and so for the units to work, it kind of makes sense that I just maybe multiply by the ratio of those two masses in a way that I'm going to get a smaller speed. If I check with my calculator what this is, it turns out to be 12 meters per second. Maybe at 3 sig figs I should say 12.0 meters per second, but I'm not going to worry about that so much. All right, so there donkey gets shot. That's kind of cool that it shows us that again. And there's the answer of 12.0 meters per second. Note that when it's shot, the cannon really did move in the recoil way that we're describing there.